Download this code from codegive.com, link in the description below. OK, let's dive into common coding mistakes, why they happen, and how to avoid them, along with practical code examples in a few different languages to illustrate the concepts. I'll focus on mistakes that beginners and intermediate programmers often make, leading to bugs, performance issues, or unmaintainable code. Tutorial: Common coding mistakes and how to avoid them. Introduction. Writing code is more than just making it work. It's about creating solutions that are robust, efficient, readable, and maintainable over time. Many developers, especially those starting out, fall into traps that lead to significant problems later on. This tutorial will cover several of these common mistakes, providing explanations, examples, and practical advice to help you write better code. 1. Ignoring or poorly handling exceptions. The problem exceptions are runtime errors that occur when something unexpected happens in your program, example trying to divide by 0, accessing a file that doesn't exist, network connection issues. Ignoring exceptions or handling them improperly can lead to crashes, data corruption, or security vulnerabilities. A common symptom is code that seems to work, but fails silently or produces unpredictable results under certain circumstances. Why it happens. Lack of experience with error handling. Belief that certain errors won't happen, they always do eventually. Lazy coding, it's easier to ignore errors initially. Not understanding the potential consequences of unhandled errors. The mistake, empty catch blocks and generic exception handling. Why it's bad. Hides errors. The program continues running as if nothing happened, even though a critical error occurred. This makes it extremely difficult to debug because the error is masked. Unpredictable behavior. The program state might be inconsistent after an error that's silently ignored, leading to unpredictable results later on. Security risks. In some cases, unhandled exceptions can expose sensitive information or leave the system in a vulnerable state. The right way. 1. Catch specific exceptions. Catch only the types of exceptions you expect and can meaningfully handle. 2. Log exceptions. Always log exceptions with sufficient information, timestamp, error message, stack trace, so you can diagnose and fix problems. Use a logging framework, like Log4j, Serolog, or Python's logging module. 3. Handle exceptions gracefully. If you can't fully recover from an exception, take steps to prevent further damage. This might involve rolling back a transaction, closing resources, files, network connections, informing the user that an error occurred, without exposing sensitive details. 4. Rethrow exceptions. If you can't fully handle an exception, rethrow it so that a higher level of the application can deal with it. This is especially important in libraries and modules. 5. Use finally blocks. Use finally blocks, or their equivalents in other languages, to ensure that cleanup code, example closing files, is always executed, even if an exception occurs. Good examples. In these examples, we catch file not found exception and IO exception specifically. Log detailed error messages using a logging framework. Print an error message to the console, to inform the user. Ensure that the file is closed in a finally block. Re-raise generic exception so that it can be handled further up the call stack if needed. 2. Ignoring resource management, memory leaks, file handles. The problem. Many resources in a program, memory, file handles, network connections, database connections, are limited. If you don't release these resources when you're finished with them, you can run out of them, leading to crashes, performance degradation, or other unpredictable behavior. This is known as a resource leak. Why it happens forgetting to free allocated memory, in languages like C/C++. Not closing file handles or database connections. Not releasing network resources. Relying on garbage collection without understanding how it works. The mistake, allocating memory/resources without freeing them. Why it's bad. Memory leaks. C/C++. The program consumes more and more memory over time, eventually leading to a crash or system instability. File handle exhaustion. The operating system has a limited number of file handles. If you don't close files, you might reach the limit and be unable to open any new files. Database connection starvation. Similar to file handles, database servers have a limited number of connections. If you don't release connections, you might exhaust them and prevent other users from accessing the database. The right way. 1. RAII, resource acquisition is initialization in C++. Use RAII to tie the lifetime of a resource to the lifetime of an object. Use smart pointers, std unique _ptr, std shared _ptr, to automatically manage memory. 2. Try finally or using statements. Use try finally blocks, Java, Python, or using statements, C, to ensure that resources are always released, even if an exception occurs. The using statement automatically calls the dispose method on the resource. 3. Garbage collection awareness. Understand how garbage collection works in your language, Java, Python, C. Avoid creating unnecessary objects or holding onto references to objects longer than necessary. However, don't rely solely on the garbage collector for critical resource management, example file handles. Always close them explicitly. 4. Context managers, Python use with statements, which act as context managers, ensuring resources are properly managed when exiting the block. Good examples. 3. Hard coding values and magic numbers. The problem. Using literal values directly in your code, without giving them meaningful names, makes the code difficult to understand, maintain, and modify. These literal values are often referred to as magic numbers, or magic strings. Why it happens. Laziness, it's quicker to type a literal value than to define a constant. Not thinking about future changes, the developer doesn't anticipate that the value might need to be changed later. Lack of awareness of code readability. The mistake, using raw values directly in the code. Why it's bad. Lack of clarity. The meaning of the literal value is not immediately obvious. Someone reading the code has to guess what the value represents. Difficulty in modification. If you need to change the value, you have to find all occurrences of it in your code and update them. This is error-prone. Inconsistency. You might accidentally use different values in different places, leading to inconsistencies in your program. Reduced readability. The code becomes harder to understand and maintain. The right way. 1. Define constants. Declare constants with meaningful names to represent the values. Use static final in Java, const in C++, constant _name in Python, by convention, and const or read-only in C. 2. Use enums. If you have a set of related values, use an enumeration, enum, to represent them. 3. Externalize configuration * for values that might change at runtime, example tax rates, database connection strings, store them in a configuration file or database. Good examples *. 4. Ignoring code style and readability. The problem code that is poorly formatted, inconsistent, or lacks proper comments is difficult to understand, maintain, and debug. Why it happens lack of awareness of coding standards. Rushing to get code working without paying attention to style. Not using code formatters or linters. Not understanding the importance of code readability. The mistake, inconsistent indentation, no comments, long functions / methods. Why it's bad increased cognitive load readers have to spend more time and effort understanding the code. Higher risk of errors poor formatting can make it easier to miss errors. Difficult to maintain it's harder to modify and extend code that's difficult to understand. Reduced collaboration other developers are less likely to want to work with code that's poorly written. The right way 1. Follow a coding style guide adhere to a consistent coding style guide, example Google Java Style Guide, PEP 8 for Python, see coding conventions. 2. Use code formatters use code formatters, example IntelliJ IDEA's built-in formatter, Black for Python, Visual Studio's formatter, to automatically format your code according to the style guide. 3. Use linters use linters, example check style for Java, Pylint for Python, Roslyn analyzers for C, to identify potential style violations and code quality issues. 4. Write comments add comments to explain complex logic, algorithms, or design decisions. However, don't over-comment. The code itself should be as clear as possible. 5. Use meaningful names choose descriptive names for variables, functions, and classes. 6. Keep functions short break down large functions into smaller, more manageable functions. 7. Use consistent indentation use consistent indentation to show the structure of your code. Use 4 spaces for Python and Java and C's convention. Good examples 5. Ignoring security best practices. The problem writing code that is vulnerable to security attacks can have devastating consequences, data breaches, system compromise, financial loss. Why it happens lack of security awareness. Assuming that user input is always valid and safe. Not understanding common security vulnerabilities, SQL injection, cross-site scripting, etc. Relying on security by obscurity. The mistake, SQL injection and cross-site scripting, XSS. Why it's bad SQL injection an attacker can inject malicious SQL code into the query, potentially gaining unauthorized access to the database, modifying data, or even deleting the entire database. Cross-site scripting, XSS an attacker can inject malicious JavaScript code into a web page, which will then be executed by other users who visit the page. This can be used to steal user credentials, redirect users to malicious websites, or deface the website. The right way 1. Input validation and sanitization validate all user input to ensure that it conforms to the expected format and range. Sanitize input to remove or escape potentially harmful characters. 2. Parameterized queries, prepared statements use parameterized queries, also known as prepared statements, to prevent SQL injection. Parameterized queries separate the SQL code from the data, making it impossible for an attacker to inject malicious code. 3. Output encoding, escaping encode output before displaying it in a web page to prevent XSS attacks. Use the appropriate encoding function for the context, example HTML encoding, URL encoding, JavaScript encoding. 4. Least privilege * grant users and applications only the minimum privileges they need to perform their tasks. 5. Keep software up to date * install security updates and patches regularly to protect against known vulnerabilities. 6. Security audits and penetration testing * conduct regular security audits and penetration testing to identify potential vulnerabilities. 7. Use a content security policy, CSP. Use CSP to restrict the resources that the browser is allowed to load, reducing the risk of XSS attacks. 8. Use an updated framework * using an older framework with vulnerabilities. * Good examples * 6. Premature optimization. The problem spending time optimizing code before you have identified the performance bottlenecks can be a waste of effort and can even make the code more complex and harder to maintain. Why it happens fear of performance problems. Belief that certain parts of the code must be slow. Lack of profiling tools and techniques. The mistake, optimizing code without measuring its performance. Why it's bad wasted effort you might spend time optimizing code that isn't actually a bottleneck. Increased complexity optimization can make code more complex and harder to understand. Reduced readability optimized code can be less readable than the original code. Potential for errors optimization can introduce new bugs. The right way 1. Write clear, correct code first focus on writing code that is clear, correct, and easy to understand. 2. Profile your code use profiling tools to identify the performance bottlenecks in your code. 3. Optimize where it matters focus your optimization efforts on the parts of the code that are actually causing performance problems. 4. Measure performance after optimization after optimizing code, measure its performance to ensure that the optimization actually improved performance. 5. Keep it simple choose the simplest solution that meets your performance requirements. 7. Not writing tests, or writing bad tests. The problem without tests, it's difficult to be confident that your code is working correctly and that changes you make won't break existing functionality. Why it happens time pressure, writing tests can take time. Lack of experience with testing. Belief that testing is not important. Difficulty in writing tests for complex code. The mistake, no tests at all, or tests that don't actually test anything meaningful. Why it's bad increased risk of bugs without tests, you're more likely to introduce bugs into your code. Difficult to refactor it's risky to refactor code without tests because you don't know if your changes will break anything. Reduced confidence